So the final speaker of this session is Herman von Vlijmen, who is going to talk about HPC needs for free energy calculations at Janssen.
All right. Well, I'd like to thank the organizers for giving me the opportunity to talk here. I'm going to give a bit of a perspective from a pharma company on the value of the value of these kinds of calculations for what we do, and a bit of our experiences in actually applying it. Now, this is a very short presentation. I'm actually not going to give you too many results. I'm just going to talk to you about why these calculations are important, give just a few results, but also some thinking about what kinds of high-performance computing solutions are most relevant to us. So I work at Janssen, which is basically the name for all the pharmaceutical activities of Johnson & Johnson, which is, as you know, a worldwide healthcare company. And as Peter already mentioned, although it goes by different names, there is this method. It's one implementation of it is called free energy perturbation. There's something else that's called thermodynamic integration. But it's basically a rigorous method to calculate the free energy of binding difference between different ligands binding to a particular target, usually a protein. And this is a somewhat more colorful picture of the same thing that Peter already showed. And it basically it goes to the point that it's really based on statistical mechanics. It's a rigorous method in which ligands are chemically transformed into one another, both inside the protein and in solution. And the result out of that, you can actually really get the free energy difference of binding between compound A and compound B. Whereas the direct path of just actually taking your small molecule here and letting it bind to the protein, to actually calculate that has so much error involved that it's really much more difficult to get even a reasonable value. Why do we need it? So this is really, okay, this is all nice, and you could say this method has been around. Actually, the whole concept was out there in I think the 30s of the 20th century. People have been running these calculations since the 80s as well. But it hasn't really been very practical, and I'll get to that. Why do we need it? So I'm heading a computational chemistry group at Janssen, so we do this all day. We do molecular design all day, try to predict what the activity will be of a compound that hasn't been made yet, and try to come up with the next best compound to make to speed up drug discovery. So we do need ways to better predict these affinities, because actually we're not good at that. We're really not good at that. Even though some people might say that they are good at it, they're not. It will actually change how computational chemistry impacts compound optimization. If we had a much better trust in the predictions that we make, with maybe even a confidence interval, you can actually start making suggestions to chemists that are maybe not very straightforward. So, first of all, if your predictions are better, obviously a higher percentage of compounds that are actually synthesized will have good affinity. But also, when I say better compounds, if you're more certain about your predictions, you just have a lot more. There's much more reasons for chemists to actually make something that they don't really like to make because it's more difficult synthetically. And this is usually what we run into. Chemists will usually make the things that they can make relatively easily, and we're not certain enough of our predictions that we can say, no, you should spend 2 months making this compound instead of 2 weeks making that one. And that will be a major difference, I think, if we can get these better predictions. The other one, and Peter also referred to this, is there's this whole, of course, there's many statistical methods of also predicting compound activity, which are inferencing methods, which are only good at interpolation between already known compounds. But we need to go outside of what we have already done. So if you want to do that, you need to go back to the physics that underlies the binding of it. Otherwise, because you don't have any examples in the space where you want to look for a molecule. And the last thing to notice here is that it's actually important in all phases of optimizing compounds. You know, we have these names for the different phases, where hit to lead is where you have your initial hits, micromolar hits that you try to get to higher affinity, let's say low nanomolar binding affinity. But also later on in lead optimization, where there's other aspects that become very important, like maybe acting properties, so the pharmacokinetics or even toxicology. Even in this phase, you do want to make sure that the changes you make are not negatively impacting your affinity, because affinity remains a very important property of your molecule. So being able to predict that is really important from the start, where you have your first hits, all the way to the point where you say, well, now we have a molecule that we want to prepare for to go to the clinic. And so if we can do that better, we can do it faster, this has a major impact. But it is hard if you want to do this, because it's a very complex event that you're trying to predict. There's these systems, as you know, they're very flexible, so there's protein and ligand conformational changes when a ligand binds to the protein. There's solvent everywhere, and solvent rearranges itself with all kinds of energetic, entropic and enthalpic effects. There is this thing called entropy-enthalpy compensation, where if you start binding to something more strongly, you immediately also make the system, in many cases, a bit more rigid, which then you lose this entropy, which is just counterbalancing what you just tried to do in terms of free energy. So this is something where you cannot just by looking at a system or doing a simple calculation see which one of the two will win out in this effect. And then there's, of course, electronic or quantum effects that we're not going to talk about today, but these are important, and they can also have a big impact. What are we doing? And this is just definitely what we're doing today. I mean, there's lots happening, so I think this might be a different slide a year from now. But what we're doing today is we have a license to a company who's called Schrodinger, has a workflow. It's called FEP+, Free Energy Perturbation Plus, which is based on the Desonant Molecular Dynamics engine, which we are using quite extensively today. We also are exploring the use of other MD engines. MD is one that Peter already mentioned. He also mentioned Amber, he also mentioned Bromax. There's another one called OpenMM. So these are all other MD engines that are also developing their free energy perturbation and thermodynamic integration methodologies. We are working with Peter, either, actually we did it independently, but also within the Biomed project on his thermodynamic integration method that he already mentioned, but also on his SNEX method, which has the continuum electrostatics. We also do some of that internally in a different tool that we developed ourselves. What we have as hardware, this is sort of where it gets more of a high performance computing link, is we did buy two 48 GPU clusters of NVIDIA. It's mostly K80s, we do have some K20s in there. So there's one in Belgium of 48 and one in the US of 48, and that's what we use because the FEP Plus software has been optimized to run on GPUs, and it actually performs quite well on that. We do have access to a virtual private AWS cloud, which now also has NVIDIA K80s, where access is basically, it's not unlimited, but it's a fair number of K80s that you can access that way. And of course, we are exploring options with supercomputing centers via Biomed, but we're also doing that. We did that before, just to see, well, what's the most. Basically, we're exploring, what's the best way for us to do this. Collaborations. Well, we obviously work with the Schrodinger scientists. We also work with Peter. We have some other funded projects to look at specific targets, but in most of these, in all of these collaborations, free energy calculations are quite central. So we're active in this area. And we're currently doing a large-scale perspective calculation of around 1,000 compounds. So that's quite a large number. I mean, remember Peter in his presentation talked about, some of the stats he showed were, I think, for 25 or 30 compounds or something like that. 1,000 compounds, that's quite a lot, and so for that we're currently doing that now on the GPUs that are available at AWS. Biomed is the project obviously that we're a partner in. What are we planning to do within that project. We have a postdoc that will start in a couple of months, and basically, you know, I'll get a little bit to that. The focus still is the postdoc obviously needs to develop methodology or really understand things or develop science and not just run calculations from an already standardized workflow. So we're really interested in seeing how these methods do on, you know, really cases that are not really predictable with any other methods. You know, there are these things like activity cliffs where you make a very small change in the molecule has a major effect on the free energy of binding. Why is that? Quite often you just don't know it by looking at it. But in principle, free energy calculation could predict that. Cases where you see major solvent rearrangements when you change the ligand a little bit, or these large differences in entropy and enthalpy of binding that you sometimes see in systems. These are things that, again, we cannot predict in any other way, and we're very interested in being able to predict those. And that requires, you know, quite a bit of computation, and I think the Biomed project is with all the HPCs in there, is a perfect way of really doing the science to bring the science forward there. And then obviously also cases where the free energy predictions are really bad. Those exist. You know, it's not always, doesn't always work. Peter's way of actually averaging over 5 or more different initial velocities is already a major step because you can see what the variability is. But sometimes even, you know, just don't get it right. And why is that? And we'd really like to understand that because it will improve the method. And then, of course, take a look at other methodologies. So this is these are just 2 slides that show you what's a realistic case. So this was a case in a phosphate esterase 2, which was an internal project, which is an internal target. And this is for a number of compounds, actually the kinds of correlation that we got, which you can argue, well, is this good enough? It actually is good enough to actually do something with that's highly productive in drug discovery, because our next best method that we had to do this, which was a highly optimized docking score that we had developed over quite a while, was this. So this basically tells you, and this is more or less the reality of trying to predict the affinity of compounds in a lead optimization stage, where you're making small changes to the molecule and say, well, how much would what would the difference be if I would add a methyl or if I would add a chlorine in this position? This is the kind of correlation that you can expect from most predictions, which is basically no correlation. So this is why I'm saying we're not good at this. We really aren't good at this, and we need these free energy methods to do this. So what do you need? Some of these numbers may not be completely accurate, but I think it's in the right ballpark. So a typical transformation between 2 compounds, and this is just a graph that you get if you use the Schrodinger software, that basically where every box here is a compound, and then every link is a transformation that you do from one to the other, which is one of these, which is basically the basis of the free energy perturbation method. A typical transformation, the system basically involves more than 10,000 atoms, and you need to do more than 10 million time steps. And this basically and these are all atoms that are interacting via fairly complicated potential energy functions. So this kind of gives you an idea why you need these a lot of computation to get this. On top of that, it's actually to basically improve the consistency. There's a couple of things you can do. One is what Peter is doing, which was described in this paper, where you use different initial velocities just to get a sense of what's the variability here. Another one, and ideally you should use both of them, is to make a lot of different transformations between compounds. Not just saying, well, I'm gonna assume that I'm gonna read off my affinity for this compound by just making the change from this compound. No, I'm also gonna make the change from other compounds. And because free energy is a state function, in theory, if I take this path, the number should be the same as if I would take this path that goes via a few other compounds. So that's sort of another type of averaging, and we have definitely seen that internal consistency improves when you use that type of averaging as well. But it means that you have to do multiple transformations per compound, not one, but let's say 3 or more if you want to even do that better. So if we use the Schrodinger's FEP software, FEP Plus software, it takes about 24 GPU hours for one compound transformation. Which means that on our GPUs that we have right now at Janssen, we can do about 30 compounds per day. That's sort of a ballpark number. If you look at the Thai software that was described in this recent paper here, which I think that's the work that was done at Archer, it took about 8 hours on 6,200 cores per compound transformation. So what that means is you can do about, I guess it's not exactly right, but it's in the same order of magnitude is correct, I think 20 compounds per day on all of Archer. So, just gives a bit of a comparison. So 100 of the GPUs that we have give us 30. There's 20 on Archer that you can do on a day. I must say that in this particular paper, he did a 5-fold sampling. So he basically did 5 times as many transformations than we did. So, as I said, these numbers are not directly comparable, but I think the ballpark is correct. So real-life discovery compounds, that's already mentioned, 1,000 compounds that we are already now exploring on our simulation. This is more realistic, so 150 compounds, because the reality is, okay, you're in this project, the chemists are asking, well, what compound do I make next? I have all these ideas, but I don't know which one will be best. And unless we do this, we don't know either. I mean, we can do this interpolation, that works, but if we want to have some really different chemistry, we have to use these methods. But then 20, 30 compounds, if you do 20, 30 compounds a day, that's not really the level that you need. You need to actually be able to do much more. And so, for instance, this is just, if you ask any chemist in that PDE2 project, what are the things that you could make right now that you have in mind, you easily come up with 150 compounds. And this is one project. We have 25 projects going on at any given time. So you really need more computation to deal with that. And currently we are actually also, this is for one project, we're exploring these over 1,000 compound proposals, which is actually quite reasonable, a number to have. And then on top of that, you would have an ideal turnaround time for these calculations to be less than 2 weeks. As I said, the analogy of the weather forecast. If I predict this in 2 months, the chemists have already started with the whole synthesis plan. It doesn't work out. 2 weeks is quite reasonable. If we can work on something for 2 weeks, they can sort of think about how they will do the synthesis, and they will wait for that. If it's more than that, they won't wait for it, and you can only do some partial. You can only have a partial impact. So how realistic is this? So as I said, these are the numbers that we can do today, either on the GPUs or on a system like Archer. If you look at the cost, so this is just taken straight from the AWS cloud. So if we, let's say 96 GPUs, let's say that's about 100, cost that, which means $800,000 per year for us to do that. And what can we do with that? We can then do 30 compounds a day. That would be purely the cost of the compute power. It doesn't even include the licensing costs that we also have to pay, but let's say just focus on the compute power. And 30 compounds a day, I would say it's reasonable for average demand today, but as I just said, if we can actually make these predictions work, and it will generate a much higher demand, and it will actually change the way we do drug discovery by making it more compute-centric, then 30 compounds a day is not going to be enough, definitely not enough for the whole company. It would be maybe enough for a couple of scientists, but not for the whole company. Because then also at peak times, you want to do these higher numbers and then do that within 2 weeks. So for that, you would need 4 to 8 Archers available to you, or you would need this level of GPUs. And you can already see that's actually quite expensive. Actually, it's my last slide, so fine. So about the method, I don't think I have to explain further that this is actually a very important thing for us if we can make this work in a in the right amount of time. We have already used it in a number of projects. I just showed two here that we've published on, but there's many more that we're currently using on. I do think that further development of the methods, the workflows, the protocols is necessary, and this is what we're really interested in within the Biomed project. Right now, it's kind of limited by our cost-benefit balance. There's actually quite a few pharma companies that have not stepped into this because they say, well, it's not yet accurate enough for the cost and the effort that we have to go through. So we have stepped into it, but we realize that it's definitely not an easy sell to make this with the current level of prediction and the current level of cost. So this needs to improve. And well, part of the improvement will of course be because the compute costs will continue to drop, so that will help us very much so. Especially if you use more GPUs, I think it's probably be a cheaper option than using the standard cores. And also the methods that will improve will make that cost-benefit balance also better. But this is where we stand today, and I think this is the last slide. This is just just the tables from the AWS cost where I got the numbers from for the GPUs. So with that, thank you for your attention.